So in the last video, I introduced you guys to the idea behind transformers and what transformers do and how transformers use different numbers of coils or loops of wire to change the actual EMF that actually can be used based on how many coils you have as a ratio actually. And I sort of have the little blurb that we have from the last video in the top right hand corner there. Same type of thing. So if we look at sort of like transformers, in general, basically what they do is transformers can actually change the EMF or the voltages, whatever you want to call it, based on the ratio of loops that's actually used. Okay, and this is what we were talking about last time a little bit. So again, this is the one I showed you last time, the type of thing that you plug into your wall. Believe it or not, originally cell phones were never actually designed to be plugged in at home. They're more designed specifically to be charged in your car as a portable phone. And of course, car outlets are 12 volts, and that's why they're designed to use 12 volts, as well as a lot of other things. So that's why the plugins or the plugs look the way they do. So transformers, anytime you like a little electronics, that little box to plug into the wall, there's probably a transformer inside. And it's a pretty simple induction type thing. You got a chunk of iron, a couple coils of wire, and you can change the voltage. And that's basically what transformers do, is they change the EMFs and voltages based on the coils that are being used. And it's all about the ratio. So if you have 3 times more coils, you will get 3 times the voltage. If you've got 100 times the coils, you'll get 100 times the voltage. Of course, if you cut it down to half, you'll get half the voltage. It's all the same ratio. It's actually a really, really, really simple idea. So basically, the ratio of the number of loops is equal to the ratio of the voltages. And these were here, the first side. These are often called this is often called the primary side, and these would be the secondary. So you've got a primary side, a primary number of turns, a primary voltage, and you got the secondary number of turns, the secondary voltage. So you have something that looks like that. So it's a really simple idea, used for tons and tons and tons of different things. You see transformers on poles for like major power lines and stuff like that all the time. They're in all electronics, they're everywhere. They're just used for lots of different things. Now there is sort of a catch to this though. You're increasing and decreasing voltages, but there's sort of like a trade-off going on. One thing you got to be careful of though is when you do this type of thing, you must absolutely conserve energy. You cannot gain or lose energy. You must conserve energy. And of course, when you talk about electronics and electricity and all that kind of stuff, probably the most commonly linked quantities to this is power, because power is the rate of energy use or creation, whatever you want to call it. So power is the rate of energy. So the amount of energy has to be the same on both sides, which means the amount of power on both sides also has to be the same. So if you go back to what we did before, the basic way to calculate power, there's sort of two. There's energy divided by time, because it is defined as the rate of energy use. But another one that we had way back when is do current times voltage, is the product of the two. So if our power has to stay the same, we have to have a constant energy, constant power. This can't change. And this doesn't change, obviously. We have to have constant power, which means, for example, here we had the voltage go down. If the voltage went down, the current would have to go up in order to compensate by the exact same ratio. If the voltage gets 5 times smaller, the current will have to get 5 times bigger to have the same power, and vice versa. It doesn't make any difference. One will change just as much as the other. So it's sort of the trade-off. As one gets bigger, the other one gets smaller. So the current and the voltage, they sort of feed off each other to have constant power. Okay, so if voltage goes up, then your current actually goes down, and vice versa. If your voltage goes down, your current is going to go up, so they still always multiply to the same amount of energy and power. Okay, so if we go back to the ratio we have over here, if the number of coils gets bigger, the voltage is going to get bigger, but the current is actually going to get smaller. So you actually will often see the ratio written with currents as well, but the currents will have their values inverted compared to the others. Okay, because if coils gets bigger, voltages get bigger, but currents are then going to get smaller in order to compensate. Okay, and then if you even get even nerdier, also if you cross multiply I1, V1, I2, V2, those give your powers, they have to be equal to each other. So that's just another little aspect of it. But that's the basic idea behind transformers. It's a really, really simple idea. They work really well, used for tons and tons and tons of different stuff. So let's practice this a little bit and sort of show you how this works. So we sort of drew a little thing for a transformer. The circuit symbol for a transformer is often something like this, which represents a core of iron with coils of wire either side. And let's hook this up to a 200 volt power supply, something like this. And then we'll have go through a transformer, and we'll have it go and hit a resistor. And let's say we have got 600 turns on this will be the primary side, and let's say we've got 1500 turns on that side, and let's say this is a 350 ohm resistor. Okay, and I'd like to know how much current is on this second side. Okay, so really, really simple idea, not that big of a deal. Okay, now if we sort of label what our different things would actually be, this would be my primary side. It's my first side. That's my source side. And this would be the secondary side. So this here, this would be my primary voltage. This is my primary turns. This is my secondary turns. And of course, this resistance just on the second side. All right. Well, really simple. If I just use the ratio type stuff, I use my basic ratios. I know that for a transformer, N1 over N2 is equal to V1 over V2. Well, I have my two N values. I have my first V value. I can easily find the voltage on my second side. Now, this right here, it went from 600 to 500. It got 2.5 times bigger. If there's 2.5 more turns, my voltage has to get 2.5 times bigger. And 2.5 times 200 is 500 volts. Or just plug them in there, cross multiply and divide. It'll all work out just fine. So this has to have 500 volts on it. So now that I know that is 500 volts, I can find out my current. Because I've got my voltage, I've got my resistance, I can use Ohm's law to find out what my current must be. So I've got that 500 volts, I've got the 350 ohms, so 500, divide that by 350, and we've got about 1.43 amps going through the secondary side. Okay, well, let's expand on this a little bit. What is the current on the first side? What is the first current? Well, first of all, I can just look at it a little bit here. I've got 1500 turns down to 600 if I go backwards. If my turns is going to get smaller, my voltage gets smaller, my current is going to have to get bigger. And you can set the ratios again. It doesn't make any difference, but if you set the ratios, you could do N1 over N2 is equal to V1 over V2 is equal to I2 over I1. You calculate the power on the first side and the second side, they have to be equal. There's lots of different ways you can go about it. It doesn't make any difference how you set this thing up. You could have, done the I times the V. You could have done the 1.43 times the 500 to get the power on the second side. That would also be the power on the first side. You find the current that way. It doesn't really make any difference. But if I just go back to this thing right here, if I'm going to find the current, I'll just use that ratio right there. It doesn't really matter. I will just take maybe I2 V2 divided by V1, and that should give me my current. And it gives me about 3.58 amps. So I've got 3.58 amps on that side. Okay, which looks about right. Okay, so when on the primary side, when it went from the primary to the secondary side, the number of loops got bigger, the voltage got bigger, and the current got smaller, going from 3.58 down to 1.43. And all of them would change by the exact same ratio. Okay, all right, so let's try another one. Okay, so let's try this one. We've got a transformer hooked up to two resistors. This one's got 12 volts and is a 5 ohm resistor. This one down here is an 8 ohm resistor. Got a little series circuit going on. 1600 turns, 2400 turns in the primary, and we're looking for that primary voltage. Okay, so let's see if we can piece a few things together. Well, this has, it's all part about circuits and that type of stuff. So I'm going to start where I got the most information, which is at that top resistor. I got the 12 volts and got the 5 ohms. So up here, what I can do is I could find the current in that resistor just by using Ohm's law, by taking the 12 and of course dividing it by the 5. And if I do the 12 divided by 5, I can find out that there is 2.4 amps running through that resistor. Well, since this is a series circuit, if I got 2.4 amps up here, it's going to wrap around. I must also have 2.4 amps down there because it's all part of the same line. So now that I have that, I can use that to calculate how much voltage is down here. So the voltage down here would be, I times R, good old Ohm's law. If I multiply those two together, I've got 19.2 volts down there. All right, so now that I have my two voltages, if you remember in series, we take voltages and we add them up. I've got 12 volts here. I've got 19.2 volts there. If I put them together, this must be 31.2 volts. So that would be my secondary voltage, would be 31.2. All right, well, now that I have that, I've got my primary turns, I've got my secondary turns, I can find my primary voltage, right? Because N1 over N2 is going to be equal to V1 over V2. I've got the N1, I've got the N2, I've got V2. V1 is the only thing I don't have. So just using the basic ratios, I can find my V1. And we just do the cross multiply and divide. We got 46.8 volts. So we got 46.8 volts over there. Okay, so that would be the primary voltage. Now we could also do the same type of thing. We could also find the primary current. So what is the primary current? We could do that as well. And I am going to do, I'll try and do it a little bit different way. I'll try and use the whole power aspect. I know that power number 2 would be I2V2. So I have my primary or my secondary current of 2.4. So 2.4 multiply it by that 31.2, which was the voltage on that side right there. So if I put those two together, I'm looking around 74.9 watts. Now remember, that is the one thing that stays the same. Power 2 has to be equal to power 1 has to be equal to I1 times V1. So I have my V1, that's the 46.8. So if I take that exact same power of 74.9 and I divide it by the 46.8, which is my primary voltage, my primary current ends up being around 1.6 amps. Okay, so I had 46.8 volts. I go to the secondary, my voltage got smaller. I had 1.6 amps on my primary. I went to the secondary and my current got bigger, which makes sense. As one gets bigger, the other one gets smaller. Okay, so again, there's some basic transformer type calculations. Again, it's all just about ratios. That's all it is. It's actually relatively simple. Use your quantities, try and match them across, and it works really, really well.